Okay, so the next talk is about Mihaly Horanyi on the exploration resources in the lunar polar regions. Mihaly, you there?
Yes, thank you.
Good, we can see you and you're sharing.
Okay, hopefully this is full screen on for everybody.
Yes, yes it is.
So actually this is a perfect place for this talk after the one we just heard about impacts and whether or not ice can survive in permanently shadowed regions against impacts. So of course we know about impacts, you know about meteor showers and of course the sporadic meteorites here on Earth. These are, you could see them as shooting stars. Our best estimate is remarkably uncertain. It's somewhere between 50 and 150 tons of cosmic dust rains down on Earth every day. If you take that to the moon, that's about 5 to 15 tons of material that is hitting the lunar surface. There is no atmosphere. So when we enjoy, shooting stars on Earth, you will generate impact plumes of outgoing small particles, puffs of dust that in response to the incoming high-speed zodiacal type dust particles. We actually had a chance to explore or learn about this ejecta cloud of small particles. There was a mission, the Lunar Atmosphere and Dust Environment Explorer, September 13, April 2014. It made science measurements for about half a year. And it had a dust instrument in addition to a UV camera and a neutral mass spectrometer. Here I will only talk about the dust instrument itself. So we arrived and we spent about a month or so at a height of 250 kilometers. Then it dropped down and most of the mission time was spent somewhere between 50 and 100 kilometer height above the surface. And as we flew around the moon, the incoming particles had high enough speed, 1.6, 1.7 kilometer per sec, that when entered the instrument that is on the bottom right, hit our hemispherical target, which is about 6 centimeters in radius. So the whole instrument has an effective surface area of about 100 square centimeter. They generate, at that speeds, they already generate a puff of plasma, electrons and ions. The electrons are collected on the target. The ions are collected via guiding electric field into an ion detector. And the shape and magnitude of those signals would tell us about the size of the particles. This is all the data that we collected. On the x-axis is time, on the y-axis is the daily average impact rate. So particles as small as about 0.3 micron, that was near our threshold for detection at that speed, hit our instrument once per minute. Little bigger particles with radii about 0.7 microns or so, you have to wait every 10 minutes. You have to wait 10 minutes to get an impact. And then there are these special periods, which is subject to a different talk, during the meteoroid streams, where the dust ejecta cloud puffed up and became much denser, like during the Geminids or the Quadrantids or the Northern Tarids. These were the meteoroid streams that hit near the equator of the moon during the period of time when we made observations. Chang'e landed in December of 2013. We had not seen any effect, but please remember that Chang'e landed way up north, far away from us. And the ballistic trajectories of these particles will not allow you to have mixing over such a large range in distance. So what we found is that there is a permanently present cloud of dust with a scale height of about 200 kilometers above the surface. We could actually build a full model based on our measurements. On the left is all the data. Some of the black regions are the ones we never visited or we could not make measurements for various reasons, like time sharing with other instruments. Also, we could not directly look into the sun, so there is a quadrant that we could not measure. But on the right is the full model. That is our best understanding of the cloud that is engulfing the moon at all times, generated by incoming dust particles. So imagine that there is a particle that hits and generates a plume. And this is kind of a cartoon. The spacecraft is this white dot moving left to right. And then our impact rate is this funny shape because, of course, as you approach a plume, the particles are flying into this instrument. The impact speeds are somewhat higher. The thresholds then are somewhat slower. And in a couple of minutes, of course, then you fly on the other edge of the impact plume. And by then the densities drop and those are particles that are running away from you. So the threshold is somewhat higher. But as a function of height, you can figure out these plumes, and there's a beautiful organization that it takes longer at a higher altitude. These are the impact rates sorted in altitude. And the higher you are, the longer it takes to fly across a plume. So using these plumes, and actually we don't even need a full plume, just a fraction of the plume, you could figure out where are these particles coming from? What was the site where the primary impact occurred that raised this plume from the surface? And that's the concept how you could make a chemical mapping of a planetary body. There is an instrument being built here. Sasha Kempf is the principal investigator here at University of Colorado. It's called the Surface Dust Analyzer, which will fly and have close encounters, repeated close encounters with Europa. And either the plumes, if there exist, from other reasons, geological activity, or for certainly by generated by incoming particles, there will be dust particles raised from the surface. We have seen and identified these clouds around all the icy moons of Jupiter by the Galileo mission, so we know that they are there. And then this allows you to trace them back to the surface, and then you could identify the makeup. You could identify regions that have possibly different makeup than the rest of the environment. So the rest of the talk, I would argue that the very same principle, we should consider using it at the moon. Imagine that you would have a spacecraft on a polar orbit and fly over permanently shadowed regions. I have to remind you that permanently shadowed region means solar wind and UV radiation. There is no permanently shadowed anything as far as the incoming dust fluxes are concerned. Interplanetary dust will come and hit the surface at all places at all times. So then imagine that we get to fly over these beautiful permanently shadowed regions where volatile transport allowed us to collect all valuable resources, or even just even kind of the geochemical evolution of the moon is somehow recorded in there. The impactors are excavating dust from these spots, and as you fly over it, you could make measurements. And not only the size and the speed distribution, but also the makeup. So yes, I will get to finish in a minute or two. This is LDEX Plus. Imagine that instead of LDEX, we fly an instrument that the impact generated plasma is turned into or used as a time of flight mass spectrometer input. This was done on Cassini. Cassini was a linear time of flight measurement with a mass resolution of about 30. But on the bottom left is the ice measurements of Saturn's E-ring. You cannot confuse ice with anybody else because it breaks up into clusters of water molecules. And this comb is unmistakable to tell you that you found ice. Cassini, of course, made measurements, all kinds of interesting things, like identified an interstellar dust particle while orbiting Saturn. And of course, because of the limited spatial resolution, I cannot tell you what exactly are the constituents. We could guess. But a good candidate, for example, pyroxene, these new instruments could have a mass resolution that not only you could tell magnesium and silica and sulfur apart, but in some cases you could identify the isotopes. like magnesium isotopes, clearly show up as separate mass lines. So you could dig into what is in these permanently shadowed regions, identify water, and maybe even identify all the matter that we collected in there throughout history. So I think what I would like you to remember or recall, if you so wish, that the moon, as all airless bodies, are continually bombarded. The moon is, in response, is engulfed in a permanently present cloud of dust. And those particles, every single one of them, is raising a little sample from the surface to the altitude of a spacecraft, where you could make a compositional measurement, take it back to the surface, and make a surface map of where is the matter of interest. And you could certainly do this in permanently shadowed regions from orbit. Thank you.
Thank you. Excellent talk on essentially in situ sampling from orbit. We have time for maybe one question before we move on to the next talk. We'll wait a couple seconds for that. Okay, I'm not seeing anything right now. If you would, then just take a look on the chat window. There may be some questions there. It may show up over time. There is one. Yeah, we got time. From Brad Joel. Do you have an idea of the grain size of the high altitude dust?
Yes. We had a threshold for single particle detection of about 0.2, 0.25 micron, but we were also sensitive as an integrated signal for particles that would be smaller than that. I could not tell you how much smaller, but if there would have been enough, like predicted by the Apollo visual statements and whatnot, we should have seen it. We did not. So particles are submicron, and the size distribution seems to be proportional, inversely proportional to the mass of the particle. So n of m goes as 1 over m. So throughout 6 months, we had a handful of particles that were a few microns. By 150,000 detections, the bulk of those were submicron, 0.3, 0.5 size particles.
Great, thank you. And while you were speaking, several more questions showed up on chat. So if you would, please take a look at chat and respond if you can.
Yes.